Hello, everyone. Welcome to HYSKY Monthly. And while we wait for the others to join, please go ahead and type in the chat where you're joining in from today. Lovely Virginia, Cleveland, Ohio. Thank you so much, Jared. Cincinnati. Hi, Stephen. Good to see you.
Good morning.
So great to see such a global, nationwide hydrogen community showing up today. Thank you so much, everyone. And we'll get started in the next couple of minutes. We want to allow people to gather get their morning started and join us. How's everyone's morning today?
Not bad. How
Lovely.
about you?
Fantastic. Yeah. Monday morning talking about hydrogen. How great can the day get?
Fair.
Oh, we have someone from Ukraine. Hi, Psyche.
Looks like we're gonna have great attendance, Jared. So everyone's excited to hear what you're doing.
Sounds good. Yeah, my presentation is going to be more of a distillation than it is going to be very detailed, kind of like not necessarily university classroom style, but more of a building of mindset. So,
Wonderful. I'm excited to learn what exactly that entails. All right. We'll give it another 2 more minutes and start just before 10:30 or 10:35.
And if you haven't already, for those people who have come in the last few minutes, you're welcome to put in the chat where you're calling in from. Shav, I want to know where you are right now.
Rashad says he's in Hong Kong right now.
nice.
We have Renee from Vancouver, Canada. Hi, Renee.
It's Ken Swartz here. I've just put in a link in the chat to a feature story I did published on Friday in Vertical Magazine, which is a leading helicopter magazine, on my visit to Bromont to see the hydrogen electric Robinson R-44 fly a couple weeks ago. There was only 3 people invited to the event: Aviation Week, J.R. Hammond from Canadian Advanced Air Mobility, and myself, and was able to do interviews with both Mikhail Cardinal and Martine Rothblatt. I'm working on editing the videos of the interviews today, hopefully to get them up on VFS and other websites tomorrow so they can be linked. They were both half-hour long, in-depth video interviews, but the link in the chat there is to the feature article in Vertical.
And for those of you who don't not know, Ken Swartz is on the board of High Sky Society, and he's in Toronto. And Bromont is also in Canada, somewhat near Montreal.
50
So,
miles east of Montreal, and
yeah,
behind my
near
head
Quebec.
is the
Yeah.
the H2 R-44 that flew. First time they did a circuit was in April. Second time was when we were there. The more significant thing is that doing the circuit, and some of you may have been on the strategy call last week and heard this before, but the main significance is that it was a year that passed from first flight, and in that period of time, a lot of the work was really focused on optimizing the hydrogen fuel cell installation, and particularly the cooling of the fuel cell, because with the helicopter, unlike a fixed wing aircraft, there's a lot of times when you're in hover, you have static airflow, and so you have to optimize the cooling for the hover, whereas for a fixed wing aircraft, you always have that forward airflow. And it was quite fascinating. It was a great time to visit there. And this will inform their R-66 development program, which is going to be the baseline aircraft for the Transport Canada Supplemental Type Certificate program.
And United Therapeutics is done amazing work, and Shola just joined us. He's also on the board of High Sky Society from United Therapeutics.
Amazing. Thank you for sharing, Ken. I appreciate it. And good morning or good afternoon or evening, depending on where you are in the world. Welcome to High Sky Monthly. And thank you all for joining us today from all around the world. My name is Bianca. I'll be hosting your webinar for today on behalf of High Sky Society. And Sayana is also here with me. Before we begin, I just like to say a few housekeeping items. Today's session is being recorded. Also, please feel free to use the chat throughout the webinar. Submit your questions for our speaker, Jared. and you'll be able to unmute at the end of the chat to ask your questions. We'll save time at the end for Q&A, and please, again, I know everyone's tuning in from all over the world. Please keep yourself muted during the presentation so that we allow Jared time to speak. Getting into our mission, at HYSKY, our mission is to decarbonize aviation and aerospace through the use of hydrogen. HYSKY Society is a 501c3 nonprofit charitable nonprofit dedicated to accelerating hydrogen aviation through connection and community advocacy, awareness, of course, education. Our core programs include HYSKY Connect, HYSKY EDU, Flying High, HYSKY Monthly, and our HYSKY Pod. And our vision is simple. We want to have clean skies for the future generations through hydrogen-powered flight. We support the entire hydrogen aviation system, from hydrogen producers and fuel cell developers to uh, aircraft innovators, researchers, regulators, and anyone passionate about sustainable aviation. And before I allow Jared to speak, I'd like to mention a little bit more about what we're doing here at High Sky. We have Flying High, which is returning 2026 in November. We have early bird registration, which is officially open. We have a 25% discount for your ticket if you register before June 30th. I'll include the link here below. Also, if you feel passionate about aviation and you want to continue to support what High Sky is promoting, we also have an opportunity for sponsorship. I'll include the Calendly link below, and you can speak more with me and Danielle about that moving forward. We'd also like to highlight the upcoming 20th anniversary of Electric Aircraft Symposium, taking place June 18th through June 19th at the University of Wisconsin-Oshkosh.
Hey, Bianca, I'm so sorry. If you are intending to share, we're not seeing anything.
Oh, I'm so sorry. One moment.
Sorry, I should have said something sooner.
Thank you.
Sorry, no, that's your script we're seeing now, but you
Oh,
have some
let me see.
presentation slides or not? If not, that's fine.
No,
It's
one
fine.
second. I
Totally
should
fine.
have
Sorry.
the link up here. Okay, wonderful. And today I would like to introduce our distinguished speaker, Jared Semik. He is the founder and CEO of Interium Aerospace. Jared is a Marine Corps and Army Wing aviation veteran with 20 years of aerospace and independent research development. He holds 3 patents across aviation and energy conservation technologies and is the development engineer behind Ethereum, Archangel Power Propulsion, and platform architecture. Jared is a strong advocate for holistic systems and engineering and believes the next generation of technological capability across industries will emerge through integrated systems level thinking. Today's presentation is titled Beyond Component Optimization: The Necessity for Holistic Systems Engineering and Organizational Structure. This session will explore why optimizing individual technologies alone is not enough to scale the future of advanced aerospace systems, and why organizational structure and systems integration are becoming increasingly critical in hydrogen aviation across generational flight. We are honored to have Jared with us today to share his experience and insight with the High Sky community. Please give your virtual round of applause and welcome Jared Simic. Jared, the stage is all yours.
Thanks, Bianca. Well, I mean, that was pretty much kind of walked right through my own intro. That's pretty close. So I'm a 20-year veteran of aerospace. I spent a considerable amount of time in the military and deployed. I've seen a lot of which it basically informed my holistic thinking. The Marine Corps operates on basically a holistic doctrine, and it kind of experientially informed how best to make an organization and also to integrate technology together with overlap and holism to maximize your performance. Today, I kind of want to capture that a lot of that experience from both the military and civil design engineering. A little bit of a disclaimer: a lot of this, I'm going to be giving some rough generalizations, so kind of suspend judgment in the sense that there is a lot of nuance to a lot of what I'm positing in this lecture. Um, that can't particularly be addressed. So look at this in sort of the real basis of holism is the general spirit of the system and the general spirit of the take back of what you're getting. So instead of looking into specifically the details of what I'm saying, more or less understand the system of thinking that comes as a result. Um, I'm not sharing yet.
No.
Let me.
I always say I'm a visual learner, so I like visuals. They help me.
Yeah. Can you see me now?
No.
Okay, let's do this one. About that.
Yes.
Perfect.
Perfect.
Okay. All right. So let's begin with a couple of principles and axioms and definitions to basically build the groundwork for the understanding, the idea of the mindset of holism. Um, Holism in itself is both a practice and a mindset, and it lives in the space of definition. So I kind of wanted to start laying the groundwork, and then I'm going to move into some case studies so we can sort of parse out how a lack of holism has essentially made technology fall short, and how is it also improved performance, and how is that in a real world sense, how has that been capitalized upon? So first is a problem statement. Today's greatest technology breakthroughs, electric aircraft, renewable energy, IoT, AI integration, are falling short not from inadequate components, but the absent systems level thinking. In the case studies that I'm gonna show is essentially what this looks like from a comparative perspective, and also a case by case perspective of both what good looks like and what patchwork looks like. And I hesitate to say what bad looks like because it's not necessarily bad. And this is where we in the industry start running into an issue when we kind of say this or that instead of this and that. Holism brings an optimization, maximization of performance. Oftentimes, the existence or non-existence of holism, either patchwork or holism, makes or breaks the actual economic and performance viability of a technology. So let's start with a couple of definitions. Paradigm is a distinct set of concepts, thoughts, patterns, theories, and assumptions that constitute a legitimate framework for viewing and acting upon the world. So you can say this in terms of our mindset, thought patterns, theories, and assumptions. This all drives the way we think. The lack of holism in a lot of systems that we're creating from a technological perspective um, is sort of driven by the fact that we have pre-existing paradigms that have been optimized through patchwork. So once we've already created the system over time, say for instance aviation, it started out and it evolved into this paradigm and the way of thinking. The crux of this is when we start trying to change the paradigm. So this is where it becomes very crucial that we hold a holistic understanding of how to change a paradigm. And the paradigm isn't just the way we're thinking about it. The paradigm could be the system in itself. So essentially it's a system of thinking, but it's also the system. One of everybody's favorite buzzwords is synergy, but let's define it. Two or more parts whose combined effects are greater than the sum of its parts. We all sort of know this, but effectively, the reality of that is synergy is found in shared energy and function. We always talk about synergy, and this is probably one of the things that we sort of fall flat a little bit in engineering because we get very hyper specialized, we get very hyper focused on components. And in the process of improving those individual components, we do a very good job of creating new motors or new hydraulic systems and new airframes, but we don't necessarily do a good job of sharing that energy and function. A couple of the positive case studies that I'm showing will illustrate how that's actually accomplished. So this is what drives the synergy. So holism is a philosophy that systems, whether physical, biological, organizational, which is kind of goes back to what I was talking about with the Marine Corps MAGTF, is that you can have holism in basically anything. Physical, technological systems, biological, which is holistic medicine, or organizational, like Marine Corps MAGTF. ASEX, I would say, is probably a holistic organization in the way they think. It should be understood as coherent, integrated wholes. Let's pause there. So, integrated wholes is the operative component here, rather than just the sums of individual parts. And so, you're going to hear this theme emerging. It emphasizes that the system possesses unique emergent properties. That's another key axiom: emergent properties and behaviors that arrive from interaction of components. So, going back to This, the reality of synergy, is found in shared energy and function. That's the interaction of components, which cannot be understood by examining parts in isolation. This is kind of what we're doing in some of the technologies that we're producing now in humanity. A lot of it is getting the job done in terms of proof of principle and proof of concept, but it's generally falling short. And once again, holism is how synergy is created. One axiom to ponder, and this is sort of another foundational principle, is the systems are driven by an energy nucleus with unique characteristics, and I'll show you why that's relevant. Every system that we create has a driving factor. If it's a human system, it could be something like motivation of individual humans, and what is the psychology, what is the sociology of the interaction between people? That needs to be understood. It's not just the individual's contribution to an organization, it is also how those parts interrelate. Humans actually in society are probably one of the best examples of how holism works. You either have it or you don't. Good organizations often operate from a very holistic perspective in the sense that there's a lot of relationship bonding. In the military, we call it unit cohesion and morale. When you have a lot of unit cohesion, if it's an intentionally driven aspect of from the leadership, you have all of these multiplicative gains in performance amongst the people. So your team does quite a bit more with, say, 10 people working together than they would 10 individuals working in silo. So a couple of the examples of those energy nuclei: mechanical energy, like motors, engines, things that move; molecular kinetics, tongue tied. It was basically thermal energy. Electromagnetic radiation, it's not necessarily the radiation aspect, but electromagnetism. This is what you find in motors and generators, etc. All of these are subject to be converted to different forms. And then, of course, strong nuclear force, which is what you find that is the binding energy of atomic nuclei in nuclear reactions for nuclear fission. Any one of these has their own particular unique characteristics that need to be essentially built for or calibrated to. So, with respect to what is most relevant to this discussion for HYSKY and everyone in the aviation space, is energy storage mediums and their individual characteristics. So, we've gotten away with Jet A for a long time, and most of which is simply based on its characteristics, its combustion characteristics, its lack of volatility, and also its power density and specific power. So you have this, because of its molecular density, it has a very good 50-50 split almost of power density and specific power. So per given volume and per given mass, it carries an adequate amount of energy that we can convert into something like thrust and then eventually into lift to do work. When we want to change that paradigm, going back to the beginning, where we're laying the foundation of, if we want to change that paradigm, unfortunately, it doesn't necessarily work to now go back to the patchwork optimization model to change the paradigm. You have to go back to a holistic approach to change the paradigm as a system, because again, that paradigm is a system. So what we're currently facing right now in electrification of aviation is this sort of mismatch of mentality, is that we're doing a very good job, and I'm actually very impressed with a lot of the companies that are out there that are creating great electric motors, and great fuel cells, and great pretty much everything, and they're getting the job done from a proof of principles perspective. But as I'll show you a little bit later, there's essentially a threshold of viability, and when you're trying to change the paradigm, if you're ignoring those particularly unique characteristics of that energy medium, that energy nucleus, and um, you're not designing to those specific characteristics, you are not going to be capitalizing on any gains that you would get that would not exist by carrying over the old mentality, if that makes sense. It's very difficult to articulate. So what I want to show here is, so since we're all here for hydrogen, and most of everybody kind of understands that liquid hydrogen is the most um, power dense from a volumetric perspective. The issue is The specific power is very high, so we get essentially a about a 2-to-1 advantage over Jet A per kilogram for energy specific power or gravimetric energy density. The problem is liquid hydrogen is it's abysmally energy undense in the volumetric perspective. So when you're thinking of holism in terms of hydrogen aircraft, you have to understand that those are limitations. Those are also advantages. So you get this advantage, you get an advantage from a gravimetric perspective, but there's also, of course, a disadvantage in the volumetric perspective. What you need to do then is understand the entire system from that energy nucleus perspective. So if I understand that this is not the same as Jet A, I have to take what are those unique characteristics of hydrogen, liquid hydrogen specifically, and saying, okay, what are these things listed out? Hmm. And how do we best create a system that capitalizes on those? So what we need to do is carry more energy. We need to bridge the gap um, between energy stored and energy used because there's no amount of increase of volume of fuel stored for liquid hydrogen that's going to overcome that differential of power density that you get between the two. So this is sort of where it ends up lending into holistic engineering. One follow-up is in holistic engineering, the system architecture calibrated to the energy nucleus precedes the components and drives the component development instead of component development driving the system architecture, which is kind of currently what we're sort of doing. Once we have a paradigm in place, we sort of have this mindset. So in aviation, we know that we use Jet A, we use open Brayton gas turbines, we use tube and wing. A lot of the stuff hasn't really changed. And what's happening is that we're kind of in a sense saying, what are the easiest low hanging fruits to kind of replace those components? Because we already understand this is how an aircraft functions. Unfortunately, once you this actually so a little short story of Eternium is this is one of the things I identified in the past 10 years of developing the architecture for Eternium's Archangel is that I recognized that if we were to one-to-one swap using a first order Bouquet analysis, so to understand range from an empirical perspective, it was always going to fall short if I were to say use the existing components and the existing methodologies that we're currently using without actually optimizing for these particular characteristics that hydrogen or say batteries bring. So another is system efficiency and power density is a measurement of how effectively energy is converted to useful work. So let's go back to the holistic engineering axiom. So what I want to emphasize is the system drives the component development instead of component development driving system architecture. This is where I've gotten tremendous amounts of pushback from the industry. A lot of the pushback that I've received is that, okay, well, we have to de-risk at the component level because if we try to de-risk at the system level, the capital expenditure and the risk that we have at that level um, uh, is very economically uncomfortable for most. Um, this is not what this is saying. So when I say it drives the component development instead of component development driving the system, it's to say that we create the architecture tuned to the unique characteristics of that energy nucleus. And that informs all of the components that come as a result of that system architecture. That is probably one of the most important axioms to understand in holism is that it's not that you don't optimize the individual components. It's not that you don't say, for instance, like an electric motor. It's not that you aren't doing a diligence to optimize those. You could even take that as its own system and optimize that holistically. It's not that you aren't doing that. It's that there are often times, and I'll show you an example of our aircraft. There are often times that if you were to take any of those components and not overlap the geometry, the mechanical function, and the use of energy, you only get singular siloed efficiency gains or power density gains. So in terms of orders of magnitude, you end up falling short. So So this is essentially what I just said. So through mismatch of the characteristics of the energy within the system, typically underutilization, waste, and little overlap, you end up sort of falling short. So you end up getting basically a first order gain instead of a second order or multiplicative gain. So we can essentially define this as patchwork. So a couple of the case studies that I wanted to go through, and again, so disclaimer, these will be gross generalizations because there is so much nuance in this. You could essentially turn this into an entire semester lecture at any university. So what I want to examine is the cases of solar wind and concentrated solar power as it pertains to the mismatch of the duck curve, mismatch of production demand. This was known very early on by the Department of Energy, and it has only slowly been recently addressed. And there's a couple of reasons why. Some of it's mindset, some of it's economics. They usually walk hand in hand. And of course, the most relevant here is electric aircraft. The patchwork and the lack of first principles calibration has led to airframes that are not competitive with the incumbent. There's a very important principle here, and I know I kind of get into hot water by pushing this narrative, but one of the difficulties that we're running into is that funding operates on the promise of competitiveness in a market and or cost reduction. It's the economics that essentially drive it. If there's essentially no competitiveness to whatever it is you're delivering on the top end, so where the rubber meets the road, not the individual systems that you're creating for it, but if it's not competitive, so that entire system, if you put that system against the incumbent, if that is not a competitive to the incumbent without some recognition to its calibration within a niche that cannot be addressed by the incumbent, and I'll show you that in the eVTOL portion of the electric aircraft case study, is that you can have essentially patchwork if you understand the system of its operation and deployment. So case study number one, deployment of solar wind, concentrated solar power. So let's talk about the promises. So this is kind of what we're driving towards is goals. So the promises of solar wind and concentrated solar power is free energy. So it's not necessarily free because we all know this. We have to spend money on the equipment. But once the equipment is purchased, the energy is essentially free. It's ambient. It's ambient to our celestial selves here on planet Earth. So it's renewable and exhaustible, which is to say that sun and wind it drives won't be depleted for billions of years. So, and consequently, with climate change, to the degree that is relevant, it's actually increasing some of the power, the excess of wattage within the atmosphere that we are retaining as a product of climate change is actually driving higher concentrations of wind. So, win-win for wind. Um, so no greenhouse gases. Of course, we all know this. Everybody's been drilled, with this concept for years now, during use, but only in production. And the production of hydrocarbon, greenhouse gases during production is actually pretty negligible throughout the life cycle of renewable energy. One of the emergent properties now is energy independence, and we're now seeing this on the global stage. Everybody has been fighting over resources since the beginning of time, and now it's become sort of a global affair. So after production, no further mining, drilling, refining, and no complex geopolitical alliances are necessary to continue power production. This is probably the most apparent principle with hydrogen specifically. Every specific type of hydrogen, when you're talking about, say, green hydrogen and point of use production, this lends itself very well to energy independence. So let's talk about the characteristics. So with every system in the energy nucleus, they all have their advantages and disadvantages. And this is how you calibrate the entire paradigm. So this is how you calibrate, say, in this particular case, is grid production and also cellular production, like solar and wind on houses or um, commercial real estate. So the advantages of solar is low maintenance. Of course, it's pretty much it's static. We all know this. So it's sustainable. Like I said, it comes the energy comes from the emissions of the solar radiance of the sun. That's not going to be it's not going anywhere. For billions of years. It's also scalable. So since solar panels are small, you can scale them as large or as minimum as you want. So wind, the advantages are they're very cost efficient, owing to its power density. It converts a tremendous amount of that wind energy to mechanical rotation, and then of course to electric generation. It's another advantage is dual land use. You can use the land that those sit on because of the lack of footprint. You can use it for farmland or grazing, or agriculture, et cetera, et cetera. And that lends itself into economic growth, a land lease. So you could be using the land, but you could also be leasing it to something like PG&E or First Energy, where they're essentially paying for the use of the land for wherever it sits. Unfortunately, with the good, we also get the bad. So this is what we essentially have to um, calibrate the system to. So we have to take advantage of the advantages. We have to capitalize the advantages, and we have to holistically understand the systems. And this is where most of our mitigation of the disadvantages come from. So with solar, it's land intensive, of course. It covers everything. What we're starting to do is we're starting to see um, some clever use of solar on parking structures, buildings, etc. And it's been rolling out. I think what we're starting to do is wake up to the fact that the system is not exactly how we thought it was going to roll out. We kind of looked at it from this one to one, apples to apples swap, which it generally isn't. Because going back to the core principle here is that I think we first saw it as, okay, well, we already have this paradigm. We have nuclear plants and gas electric generation and coal plants. Why don't we just take this other component and just swap them? And I understand that the engineers and the scientists didn't necessarily see this, but this also needs to get into the mindset of investors and legislators, et cetera. So a couple of the other disadvantages are material scarcity, of course. Some of them use rare elements. Weather dependent. Clouds are a problem. If you live in a cloudy place, they don't really work very well. Some disadvantages of wind is unpredictable. Wind is as unpredictable as the wind. Um, so the environmental and social impact. This also kind of goes with solar, but mostly wind. There have been issues with its impact on migratory birds, some of the local bird populations, et cetera. This is also a concentrated solar power issue with the heliostats were essentially death rays for a lot of the avian species in the area, and that was an environmental issue. Social impact. Um, one of the projects that was proposed here in Cleveland was offshore megawatt level wind turbine farms. And it essentially unanimously got voted down because everybody assumed that it was going to be an eyesore. So this is a social impact. And then, of course, ideal sites that are free of all of this, the unpredictability of the wind, environmental social impact, are generally in remote areas, and then you end up having line losses. But both of these, the issue is variability. So let's talk about the duck curve. This is where this is relevant. So they fall short because of the duck curve. So the duck curve is the aggregation of the supply and demand together. So what you see here is the middle of the day, we have a maximum of production for solar. And just as there is a ramp up while everybody's coming home from work, they're turning on all their lights and TVs and cooking food, etc. Um, that is when precisely the energy from solar is starting to fall off. So what you end up getting is this kind of a mismatch. Um, Also, we have a similar issue with wind power because of its unpredictability. So very early on in the 2010s and 2020s, when solar and wind costs fell by about 90, 70% respectively, developers treated production and storage as two separate industries. And this is where you start getting into this kind of economic mindset. And this is where you kind of start seeing an emergence of patchwork. As at the same time, battery costs remained astronomical and would have doubled and tripled the cost of each individual project. These were not developed as a system. The interesting issue is that each individual company was creating solar panels. They were a solar panel company, and wind turbines, and they were a wind turbine company, and they were getting their own individual funding, and they had their own individual economic prospectus for what is going to be the return for this particular component. The only issue is that there was very little in the way of implementation of the into the grid. There was talks of it in the 1970s. Scientists and engineers knew this very early on, that because of this duck curve, because of the variability of production versus the demand throughout the day, that they understood that there will be an incompatibility with grid dynamics and how we essentially power the modern world. Unfortunately, because I think the scientists and engineers at the time didn't necessarily push this and raise the awareness of legislators and like the executives of like a PG&E or a First Energy or any of these other power generation companies, they saw that as well, so we can't buffer this with anything because the batteries at the time were astronomically priced, and this would have delayed or completely killed the rollout of solar and wind. So instead of delaying that to allow the maturity of those batteries and the scaling of battery production to the level that it is, instead forcing that, and instead of also finding alternatives for battery storage, they proceeded. And unfortunately, what happened is we all kind of know what has been going on. I would say about 10 to 20 years ago, when we essentially started rolling out these large projects, is that we started seeing some of the failures. Is that because we weren't fully integrating these as a system with demand buffering technology, and we weren't really building our grid holistically to integrate the variability of these productions uh, methodologies, is that we ended up starting to run into a lot of these rolling blackout issues and non-economic viability, which is essentially the issue that we're running into now with Tonopah and Ivanpah concentrated solar power systems, is that they were not delivering on the expectations. They were a lot more expensive than a lot of the emerging technologies, which are consequently have been brought up specifically together as a system. Um, and by that I mean a lot of the scaling that was happening in the PV realm and also the battery spaces made it more economically viable. And instead of that being sort of a bridge, we had to essentially retroactively integrate those buffering technologies, which we weren't particularly able to accomplish. Um, so, anyways, so let's move on to electric aircraft. So this is near and dear to pretty much everyone here. Um, So let's kind of outline some promises of electrification. We all know these: zero and lower greenhouse gas emissions, energy independence, and resilience. However, as I said previously, there is a bit of an issue. So that's not how aircraft sell. So aircraft are basically sold on performance, life cycle cost, and operation cost. And there's a couple other nuances. This is why I'm saying these are generalities. So these are the most important, essentially, tricks that they sell aircraft based on. What we're seeing with kind of the patchwork is taking that old paradigm. So you're basically trying to put new wine into old wineskins. So we understand how a tube and wing works. We understand, say, a Q400. We understand the flight characteristics. We understand the weight and balance. We understand, et cetera, et cetera. But what we're trying to do is we're trying to make a proof of concept. Val has actually been quoted as saying that the only real way we're going to move forward is if we were to have clean sheet builds. Unfortunately, we as a system, an economic system of creating technologies, they don't really see it that way. We see it in terms of this risk aversion and deployment and all these other components to getting to market. Um, so what you can see here in an apples to apples comparison, the exact same aircraft, Q400, and this is what happens when patchwork is used. And not to slander Zero Avia, they're doing an amazing job. I actually highly respect what they're doing, but this is what happens when you have a patchwork. This is the difference. So if you're looking from an economics perspective, there are some issues with the cost of liquid hydrogen. What they didn't do, and what we're not really doing as an industry, is we're not bridging the economic gap by holistically creating new technology for production and also scaling, but we're also not bridging the gap in terms of performance, which is decreasing the cost per passenger mile. And what you're also seeing here is a range disparity between the Q400 running off of Jet A and a turboprop configuration. There's essentially about a 3-to-1 disparity here. So this is kind of what you're getting, is that That patchwork is yielding a lower bottom line in terms of cost of operation and also a lower bottom line in terms of performance. So the competitiveness of the entry of this aircraft, if it were to become a thing, will be far less competitive by 3x than what is already existing. This is what we're running into. So going back to what I was originally talking about with the unique characteristic, this is where holism starts to kind of emerge. So if you look at liquid hydrogen, which is what the ZeroAvia is now starting to use, same thing with Airbus, so is Eternium, is that its unique characteristics are that it's extremely cold. And I'll explain why this is important later. It also has a 558 to 1 phase expansion ratio that can be harvested. It also has a I won't say much higher, but a markedly higher adiabatic flame temperature. It's higher than Jet A, which also can be utilized for an increase of Carnot efficiency and Brayton turbines. It has a wide flammability range, so it's tunable. And this is something that we've actually used in Eternium, is that you can tune the fuel air mixture because of that flammability range. You can tune that to thermally quench the combustion to lower or eliminate the NOx production from the direct combustion of hydrogen and air below the Milankovitch. What do they call it? What did I do? There you go. Anyways, so a couple of the other components, the advantages, it's 11.4, just 11 x lighter than Jet A. So you get this great mass fraction bonus if you're fully utilizing the volume in the aircraft. Laminar flame speed, 10 times faster than Jet A. It's a spicy combustion. So you can also utilize that. It increases the power density of your gas turbine. So if you're looking at the ZA 600 and the 2000, which is what you're actually seeing here in the Q400, it's based on a proton exchange membrane fuel cell. It's using essentially an aviation grade brushless DC motor or permanent magnet synchronous motor. It uses single center tank doer, so you are now cannibalizing cargo and um, uh, seating for the fuel tank. Because there's no utilization of the wings in any of these designs. Um, it does, however, I've heard some rumor about them using the fuel for cold sink for electronics, but that essentially is where it ends. The traditional tube and wing retrofit, there are also a lot of gains that are in non-traditional, also have been proven in non-traditional planform geometries like the B2, B-21 Stealth, Flying Wing, various other MIT, NASA, I think it's the X-47 blended wing body. These start approaching about 22 to 23 LD aerodynamic efficiency. This is relevant when you start understanding the first order Briquet analysis of potential and range. So moving on to eVTOLs, this is sort of what I was saying earlier, where there's a market comparison. So a lot of the eVTOLs have essentially kind of used a bit of the same patchwork, but this is the particular case where Joby and Beta, more specifically, have found a great market niche where they're saying the disparity in range, fuel time, and the fuel energy density is less relevant to the fact that now we can get you there faster and we can do it at a lower cost per passenger mile. It's essentially very close to the same unit production price and the same passenger capacity. So you have kind of this apples to apples comparison, but what you're seeing here is an emergent understanding that even with a patchwork, um, if you look at its deployment from a holistic perspective, we understand not just the architecture of the technical system, but the economics can also be looked at holistically and to say, where are these niches that we can satisfy and what can we bring to the economics? I have to admit that I was early on very skeptical. I was a eVTOL skeptic because I come from the the rotor wing world. And when I'm thinking of helicopters, so I was an H-1 crew in the Marine Corps and CH-47 crew in the Army. So when you're talking about um, operational ranges out to 3, 4, 500 miles with aerial refueling. You're looking at that from that particular operational application, and that's what I was actually stuck on. So I identified in my own mind where I was stuck on a previous paradigm. I was stuck on this idea that helicopters have to have as maximum amount of range as possible for that operation. What I didn't quite catch until I really started to dig into the eVTOL community and the players like Joby and Berta, where they were creating aircraft that had an equivalency in the helicopter world, but they found out that we can't compete for range, but we can compete for something like urban taxis, which is where it essentially sat quite nicely in its performance and economics. So, kind of give you an understanding of how it doesn't necessarily always have to be a testament to the technological holism, but more an organizational or economic holism. So, how do we kind of arrive here? Well, I've sort of said it about my own mentality and how do we stay here. So, I want to bring up the topic of the local minimum. So, I'm also a mountaineer, among many other things, being a polymath. So, I'm going to use one of the I'm going to use a concept that we have in mountaineering is the concept of false summit. So if you set out, there's a possibility. So if you actually look, so this being an iconized person, the perspective is that we can only see this hill. So we must climb a hill. So we proceed up the hill. We eventually find our way at the top of that particular hill, and oftentimes that's where our patchwork is. This is the low hanging fruit. This is the first thing that we encounter. But unfortunately, we get to the point where we are below the threshold of viability, and then we realize that the actual summit to climb is a larger mountain, and it's usually much more difficult, and it has its own challenges. And we realize that in order to climb that summit that was beyond the threshold of viability, we must first climb down that false summit of patchwork through the valley of risk and up the holistic mountain to the top of a new paradigm. If you're following the imagery, so keeping that in mind, we move on to holistically engineered systems. So I took 3 examples, one that's really close to me, and then one that I actually two that I admire, one modern and one several years back. And I kind of wanted to outline how holism in these particular spaces was used to increase performance and or economics. So the 3 are the SR-71 and more specifically the J-58, amazing technology. Kelly Johnson was a visionary. He wrote in his book, um, so who was responsible? A liner note, he was responsible for the design of the P-38 Lightning, the U-2 spy plane, and the SR-71, amongst a bunch of other projects. He was instrumental uh, in the advent of Lockheed's Skunk Works, and he wrote in Skunk Works his disdain for patchwork engineering and patchwork mentality in the bureaucracy of defense appropriations and the way we kind of bureaucratically do business in the large OEMs. He had an issue along with what was his name? He wrote the book Boyd. He engineered the energy management concept for uh, aircraft fighter dynamics, and he ran into essentially the same thing. He spent about 20 years trying to convince the Air Force brass of his new paradigm, his new perspective, his new modalities, and how to best optimize success and best optimize the airframes that are being developed for a new way of seeing aerial combat. The other one is SpaceX Raptor engine. This is a brilliantly designed rocket engine. It's not only brilliantly designed from a technical perspective in terms of their dynamic selection, but also how they've manufactured it from Mark 1 to Mark 3 or where they are right now. So it's a testament of the virtue of combining functions. And then, of course, the one that I know the most is the Attorney Mark Angel. It's unachievable range through holism. So let's start with the SR7. So let's talk about the relevant specs. So previous to this, these specs were essentially unachievable. So prior to the ox cart, which is the predecessor to the SR-71 and the SR-71 platform as it was a production, there were no aircraft, no production aircraft that could could exceed Mach 3, and that's production aircraft. Those in use for espionage and intelligence gathering. Prior to this, the U-2 also flew at roughly about the same altitude as this, but also not at the same speed. Mach 3 plus. Um, it is I think it holds a record for Mach 3.3, but talking to some of the pilots that have flown it, said that it'll go much higher than that. Consequently, this is also the first stealth aircraft. So the first production stealth aircraft that used RAM coding, which is a little lighter note that I didn't until recently actually know. So to sort of outline what they did, and this is how holistic engineering sort of works. So if you look at it, there's a list of these overlaps. There's a list of shared energies and a list of shared components. So first one that's notable is the symbiotic propulsion and airframe. So the J58 engines were mounted in the airframe, but didn't contain the intake spike bypass door and the exhaust. So those were all airframe components, but they were also used in the J58's function to improve its thrust characteristics throughout the entire operational range. So all the way from subsonic, from 0 to 3.5 Mach, um, these components, the intake spike, the bypass doors, and the exhaust nozzle, were all designed to work in concert with the J58's individual components to add performance that didn't exist previously. So, and of course, the J58, the turbo ramjet. This is sort of, I kind of already outlined this. Is on the next slide. I'm going to go into this a little bit more detail, but not too much. Thermal expansion to seal fuel tanks. So they knew that at those high speeds that the increase of temperature on the skin of the aircraft needed to be both dissipated and it needed to be accounted for. So this is where you kind of get into this operational holism, where you understand the entire platform together as one whole. They used they created a fuel tank that, understanding because of that coefficient of thermal expansion due to that increase of temperature, they designed it specifically to seal once it heated up. So we didn't have any buckling of the airframe and any buckling of the fuel tanks. And if you've ever watched any videos or seen any pictures of these on the ground, they would leak like a sieve. And they would leak all over everything, but that wasn't the case when they were actually at the operational velocities. They also used fuel as a coolant, and also engine fluid. So I think they were using it for some. I think at one point they were using it for some hydraulic operations, but they also used it as a coolant for various system components within the aircraft. So some of the intel gathering cameras, some of the other ancillary systems that were inside the aircraft, they were actually using the fuel as a coolant. The airframe, again, on top of the airframe being a portion of the propulsion system, there's also additional performance increases of lift and aerodynamic efficiency due to the chines in the blended wing body. So this is one of the first production uses of that sort of mentality, where they basically were Kelly Johnson and team stepped back in Skunk Works and said, we need to get to this place. We have this particular energy nucleus, which they designed. So they also took the specifications, folded it back on that energy nucleus and said, hey, we need to specifically engineer this fuel for low volatility because of the increase of temperature, but we also need to have perform dual function. And then with that understanding of that energy nucleus, they could now capitalize on it to produce a high amount of thrust per given energy, and also a high amount of lift and reduction of drag per airspeed by using this approach. So what you actually saw in this entire system was all of the components were thought of simultaneously. So when you were looking at this, you had a spec list, you had an energy nucleus, and an understanding of those characteristics, and then you basically put everything in one box and designed specifically to all of those elements simultaneously. And then you had an emergence of all the components. Now enter the J58. So the emergence of the understanding that at these particular velocities and temperatures, we needed to create an entire system that created three optimized engines in one. And this getting that holistic airframe and propulsion system symbiosis or synergy, if you will. And what you have going from top to bottom is five different configurations from takeoff, from rollout takeoff, all the way up to top speed. Each of these components adjusted themselves to change the aerodynamics, the fluid mechanics, and the thermodynamics within the system, um, keeping keeping in mind the specific characteristics of the fuel to produce the right amount of thrust and reduction of drag and the reduction of parasitic parasitic drag from shock waves. So this is one emergent study. So the second case study is a Raptor engine. I'm going to kind of go through this quick. This is essentially this is actually, I think, a revolutionary design. So it used an old Russian full flow stage combustion architecture, and they thought of this. Why this is so spectacular is that the advantage to full flow stage combustion architectures is that it understood the system of thermodynamics and heat transfer such to a high degree to increase the efficiency of the burn. So you'll see this when we do a comparative of the BE4 versus the Raptor where it is now. So its evolution was also sort of holistically derived. So what you're having here is that going back to the original axioms I was talking about with holism, this is showing how combining elements and combining principles, combining energies, you transition from the original Raptor, which is essentially a proof of concept, to the Raptor 2. I'm going to show this in the next slide. And then on to the Raptor 3, where you're watching it lose weight, but also if you're looking at the specs, it's gaining thrust. So what you're seeing here is a gaining efficiency. It's dropping weight. And in the process, because there's oftentimes an inverse relationship between performance and economics, is you're seeing the cost decrease. So you get thrust to weight ratios increasing, you're getting overall thrust is increasing, you're getting mass is decreasing, which is also increasing the performance of the entire rocket system as a whole, but then you're also seeing the economics start to catch up and improve. So what you have here is proof of concept. So you took that full flow stage combustion architecture, which gives you an increase of efficiency through improved combustion dynamics, is what you end up getting by hyper leaning and hyper saturating a methylox, the methylox fuel in pre-combustors actually can then now be folded back into the expansion of the liquid oxygen and the liquid natural gas that is the methylox. They take that expansion energy, which is what we essentially use in Eternium with hydrogen, is they use that expansion energy to increase through the pressure that it produces to increase the efficiency of the pumping. Then it dumps that heated pre-combusted mixture into the combustion chamber of the rocket engine itself, now drastically improving the efficiency and reducing the unburned portion of the fuel air mixture. So what you end up having here is this you have this evolution. So you have proof of concept, combined component function and space externally. So this is where you're getting this overlap, where you're starting to see this component functions are starting to be combined. And then the Raptor 3 is where you're starting to combine all of that internally through additive manufacturing and advanced metallurgy. So they're understanding that all these principles can be combined, and you're taking the entire thing as a whole. And that is what you're seeing is the result in the Raptor 3, is you're seeing the result of that leaning, because we understand the base principles from first principles of how this drives the system, not being risk averse, because pretty much all of Elon Musk's companies are very low risk aversion. And that's where you're seeing a lot of this revolution, these revolutions, is where you're starting to see a lot of this holism, where you're combining the energy, which is what you're seeing in the full flow stage combustion, and you're starting to see that holism in the manufacturing. So comparative to what they're using in Blue Origin, the BE4, comparable thrust. You're seeing a comparable thrust. So this is kind of an apples to apples comparison. So relatively same specific impulse, but different architecture. So open combustion is a far less efficient than full flare stage combustion. And you're seeing that paying dividends in its thrust to weight ratio. You can definitely see this where you're comparing the mass. So much heavier rocket engine for the exact same, for a very similar thrust, much lower mass, and look at the cost comparison. So when you're doing things kind of patchwork, you end up having this non-integration uh, uh, advantage where that lack of efficiency and the lack of combining of components in manufacture ends up skyrocketing the cost. So what you're seeing here in the Raptor is an increase of performance, which is obviously giving you the performance increase that you want, but it also has a direct impact on the economics. So this is the closest to me. So we set out about 10 years ago. Well, I set out about 10 years ago. We integrated about 5, 6 years ago when we incorporated, is that set out with the explicit goal to create an aircraft that is competitive to the incumbent. It's basically to replace the incumbent. Well, how are we going to do that? So when I looked out into the industry, I was seeing that you had Zunum at the time, Aviation at the time, Universal Hydrogen. Everybody was starting to kind of build these patchwork designs. A lot of them were running into issues where they were not having very competitive range, and unfortunately, they had an impact on the investors because once the investors kind of understood that once the investors essentially understood that this wasn't going to be particularly competitive in an open market at a system level or a platform level, with no particular consideration, like kind of we go back to the eVTOL, no consideration of market niche or increase in economic advantage, that it was basically going to fall flat on its face. So what I wanted to do is I used the benchmark because I used to work at Gulfstream. So I used the Gulfstream 650 as the benchmark. How can we possibly use this energy nucleus of hydrogen to create an aircraft that is competitive to the incumbent? So our set points became as follows. So we had 8,000 mile range at about Mach point 0.8, which is, these are very close to the G650 at 18,000 pounds. So the G650 doesn't carry 18,000 pounds, but being a former military guy, attending to the defense market seemed to make more sense than the civil market, essentially for also um, risk mitigation and lack of risk aversion of operationally viable equipment in the Defense Department. So and then we set out to make it autonomous, multi-role, low observable, etc. Um, but one of the ideas is, how did we actually get there? This is the crux. So we make these outlandish claims of, yeah, we can make an aircraft that goes, 8,000 miles versus 500 or 1,000 or 250. In the case of Aviation, we can make one that goes out to 8,000 miles, but we had to completely rethink the way we were doing everything, the way we thought of the Führer, the way we thought of the planform, the way we thought of propulsion. How do these elements kind of come together? So what we ended up with is a blended wing body that increases wing volume integration of when you use conformal wing tanks. When you look at it from an energy perspective, and I'll show you in the next slide. So when you look at it from an energy perspective, this entire thing is, how do we, going back to some of the beginning axioms, how do we best convert the energy that is available using its characteristics into the work that we need? So I had to completely rewire the way we were thinking about the system. So what we ended up coming up with is a couple of elements. So we needed, because there was a big gap in volumetric energy density, we had to shore up that gap. So we could only carry so much more, even with conformal wing tanks, cryogenic dual conformal wing tanks that we've designed. There's only so much of an increase you can get to, and there's a way that you can actually increase the volume, um, and also increase the efficiency of the airframe itself. And this is actually what we accomplished. All of this is having to be thought as an entire system simultaneously, but I haven't even thought of the components particularly just yet. I wanted to understand how we can sort of bridge that gap. So one of them, of course, was increasing fuel storage. So that gets us a little bit closer, but then I ended up finding about a 45% differential between where we are in terms of open gas turbine Brayton cycle jet engines in terms of their thrust specific energy conversion efficiency, versus what would we get for an equivalent in hydrogen. So if we actually had the exact same 35 to 38% thrust-specific energy conversion efficiency that we have with jet engines, we would still fall short even with an increase in fuel volume. So we had to bridge that gap in efficiency. So there's a couple of things that we ended up doing to bridge that gap, and then on top of this, so we ended up finding a lot of this overlap. So we also needed to increase the efficiency of the airframe. So the L to D actually had to increase before we could increase the range according to the Breguet first order analysis. So how we accomplish that is the blended wing body that gives us an increase of volume. Couple that with conformal tanks, we actually can increase the volume of liquid hydrogen stored up to about 8,000, 9,000 gallons. So um, one of the key things to keep in mind is that we didn't incur a mass penalty per se as much as we would with Jet A with liquid hydrogen because of its the difference in density. So we gained that component in the equation. In the process of using the blended wing body, we also increased the L to D ratio. When the most significant revolution in the aircraft is really the power and propulsion system. So how do we get from the energy stored in the fuel to thrust to lift? That's the entire energy equation, and that's what needed to be recalibrated. So we started out with, okay, we're going to electrify, because if we were to use an open Brayton turbine, we would be subject to the exact same efficiencies, a 35 to 38% thrust-specific energy conversion efficiency. Most of the energy is being dumped out of the tailpipe in thermal energy, so we can't get away with that. We need to increase the efficiency and power density. So we went with a electrified aircraft, and then so in an analysis of the modeling, we understood that if we were to use a fuel cell, we could do that. But when talking to the folks at NASA Glenn here in Cleveland, um, and doing some modeling with the Straighten that Roger Dyson was working on, he recognized that per megawatt you could actually get a higher efficiency, higher power density by about 60%. So there's a 60% reduction of mass and volume per given megawatt if you go to a combined Brayton cycle. So putting all those together and adding in the most efficient way, the most power dense way of converting electrical energy to rotation then into thrust was a high temperature superconductive motor. So um, we have this integration of propulsion and airframe. We ended up finding that we were getting gains by ducting the fan and using a variable geometry, axisymmetric nozzle, where we actually getting gains in specific thrust, and being able to open it at cruise to dump the spillage drag. All of this, going through all of these components, we increase the conversion efficiency over to about 60% over fuel cell, with about a 60% reduction in mass and volume over PEM fuel cell. We increase the torque efficiency by using a patented dual rotor high temperature superconductive motor. Then we ended up using the cooling to supercool both the Brayton system, which actually expands the Carnot threshold. And I understand this is getting way in the weeds with the technical metrics, but it all kind of comes together. So as I'm outlining all of this, we're getting all of these increases by using phase change expansion energy for producing electrical energy. So what you're starting to see is this emergence of the entire system is recalibrated, saying, okay, we can use the cold energy, we can use the phase expansion energy, and we can use the combustion energy of hydrogen to both increase the efficiency of the conversion and its conversion from energy to electric and electric to propulsion and the propulsion to lift. So each one of these then becomes an issue of this. So all of this being put into the Breguet range equation is really all to say that each one of these elements is addressed by these individual components. So once we understood the entire system, is to say, hey, we have a very unique storage medium. How do we best capitalize? What do we need to do as a system before we even started thinking about these components? And then each one of these started to emerge. So we started seeing increased energy storage capacity by making our conformal wing tank. This is a cryogenic honeycomb cord composite conformal wing tank. This is a proprietary item. This is not exactly what it looks like, so nobody can copy it. But this gives us a better mass fraction by carrying up to about 8,000, 9,000 gallons because we have an expanded wing volume because of the blended wing body configuration and also the supercritical airfoil choice that we had. It created a larger cross section. It also created larger wing volume so we can carry more. How did we do that? We actually had to use the wings instead of just a center tank. So moving on. So what I was describing in the combined Brayton cycle and HTS motor, all of these combined together with on the propulsor module, you also have this can either be set on the propulsor module or it could be set in what we're calling the Creighton, which is the combined cryogenic Brayton cycle, which is highly reclaimed. So all that thermal energy is being reclaimed back into the system until we essentially use it until it makes it low quality heat energy, at which rate it's exhausted at a low temperature. Um, so that exergy of expansion can be put into the Creighton system. It increases the conversion efficiency and then into the HTS with our wide chord propulsor and then our ducting and nozzle system, which is like the SR-71, is an integration of the airframe and the propulsor system. It increases this component of velocity over thrust specific fuel consumption. This V over C um, so these are sort of ordered in like inverse importance. So your V to C is probably your third most important. Your L to D is your second, and then your mass fraction here, its relationship of your mass of fuel versus your consumption rate is actually what gives you your astronomical gains. So putting all that together, we increase also the aerodynamic efficiency. And then going back to what I was talking about, we got all these gains. We essentially achieved all these gains of increase of mass, increase of efficiency of conversion, increase of specific thrust, and then increase of efficiency by using the non-axisymmetric nozzle system. And then of course, it looks nice. So this is more of a joke slide. This is actually kind of what holism sort of looks like. This is the process diagram. So what you're seeing is a lot of overlap of energies. Um, all of these elements have been specifically calibrated to make maximum use of the temperature and pressure differentials between the different states, going all the way from 20 Kelvin all the way up to about 16 to 1800 Kelvin with combustion. And then all of that is reclaimed back and all of it, the cryogenic temperature is all used forward. So this is essentially kind of what it looks like, but this is what happens when you look at things in terms of a system. And then, like I said, all of those become your hitching post components. That becomes your component revolution. That's what ends up informing. So it looks slightly different. And then going back to the manufacturing that we saw with the Raptor motor, is that now we are starting to, in the design, are starting to combine the manufacturing in design is starting to say we can integrate the what would normally be very heavy, very bulky heat exchangers. We can integrate those into the airframe. We can integrate those into the combustion chamber and certain portions of the Brayton system, and then also so they also become essentially 3D printed, and a lot of them are composites, so they're very lightweight, but the efficiency increases because they're also point of use. So instead of having to push the working fluid to, say, a recuperator or another heat exchanger, it's basically right there where it's the heat is essentially the highest quality. So integrating those also and it lowers, like we saw with the Raptor, will lower the cost of each individual component. But we couldn't accomplish this if we didn't understand the unique characteristics of the system first. If we didn't understand and we didn't start deriving our ideals for these particular components as they were a match to those specific characteristics. So just a an illustration of the synergy where you have, this increase of fuel volume, and then all of these elements are borrowing energy and they're essentially putting back energy. And every one of these overlaps gives you what we call a multiplicative gain, like I've said before, which a multiplicative gain is essentially where your synergy lives. And you can't do that without sharing mechanics and energy. So that's the one big takeaway for this entire lecture, is that we need to understand the key unique characteristics of that energy nucleus. We need to understand the system first, derive all of our sort of creative understanding of the system, and then allow the components to emerge from there. So what ends up happening is that this also becomes a tiered rollout. So instead of now going to the Defense Department or VCs or et cetera, is that you have to keep them. And this is kind of one of the things that we're running into now organizationally, is that there's a difficulty, is that everybody wants to essentially de-risk by tech block. And unfortunately, if we're creating these tech blocks, even when they're holistically derived, if I try to lob one of those an OEM, if I try to find a Northrop or a Lockheed or an Airbus that's looking for a specific component that we derived for a system that is very specifically tuned to the characteristics of the fuel source, it's not necessarily going to give you the multiplicative gains just by slapping it into their system. And the mathematics essentially support it. And that's where I was. That's was essentially what I was outlining with the Brigade analysis. So that's pretty much all I have. I'm going to open up the questions. If anybody wants to take any of this offline, you can contact me on LinkedIn. And also directly in my email. I am the type of person that loves to respond to people's inquiries. I love to talk about this. I have now shifted a little bit into educating the industry of how holism really works and how it can benefit pretty much everything. Everything that we're currently creating that we want to build capacity for in society is on the other side of good systems thinking. And I hope I was able to bring together a better understanding of what the difference between holism is in terms of the bottom line of performance and economics and its competitiveness to in a pre-existing paradigm, and what happens when we don't quite get there, when we really sort of think of it as kind of a patchwork parts. Um, so, anyways, so suppose I could open this up to questions. Let me go back to.
Thank you, Jared, for sharing such an excellent presentation. Um, Absolutely. Like Jared mentioned, does anyone have any questions? I did see Sarah mention that she wanted to know how is this different from design for manufacturing? And Sarah, maybe you can elaborate more on your question.
Yes, I mean, supposedly design for manufacturing is really, thinking about developing or designing the product for it to be able to be produced at a massive scale or whatnot. So really thinking about just, making it look pretty, but actually making it functional. Obviously you are touching that, but you're not mentioning that. And obviously I'm wondering if there's like an extra dimension or two, um, that that is considered holistic?
Um, not quite getting with the exact question. So you're asking, how is this different from design for manufacture?
Yes.
Um, okay, so this is also, it's designed for manufacture, of course, but this is also designed for performance, because performance drives competitiveness in the economics. So it's specifically, so holism is essentially a good word for everything. So it is designed for manufacture. So going back to the example of the Raptor motor, they were designing for performance, and then there was a secondary emergent advantage in the design for manufacture. So they wanted to prove the concept and say, okay, this is how the system works. And then they improved on it by bringing in those principles of design for manufacture. So it's this and this, not a this or this. So it's an and instead of an or. So it is designed for manufacturing and designed for economics and designed for performance. All of these things go together. And that's actually the power of holism, is that you're taking all of these into consideration. And going back to the example that we were using of the eVTOLs, is that so you have to look at the entire technology as having multiple dimensions, just like people. We have thoughts and we have emotions and we have a physical body. It's the same thing, is that, for technology, we've got the economics, we have its operational fit. We also have how is it made, and what is the actual design and function. So when you're making something for manufacturing, you're making it for ease and cost reduction of manufacture. So you're saying, okay, how do we best design this specifically for that? um, for performance. So when you're adding all these elements in, which what I'm trying to say with this entire concept is, this entire mindset is that you add all of these dimensions in simultaneously, and it's not as daunting as it sounds. A lot of it is that you really just kind of have to step back, and this is why I go back to the energy nucleus issue, is that you have to really understand it from its most fundamental first principles, and then everything else becomes emergent once you understand the system. So you basically, what you're doing is you're calibrating everything specifically for the change that you want to make. Some of them, like when we went from like prop plane fighter jets to jet fighter jets, um, there wasn't much of a change because you essentially were just kind of one-to-one swapping. You could essentially use the same fuel or something equivalent. So there wasn't a necessity for holism per se. There was just, you can get away with evolving it. But when you're trying to do something that's as drastic as electrifying aircraft, the storage mediums being so different, that difference requires that understanding of the uniqueness. And what you're doing with this is essentially piling each dimension on itself, and all of it becomes an emergence. So how you can get away with doing this as an organization, and I see Albert's question about the stage of development, concept, engineering, drawing, tested components, is this is how you can actually be sort of where we are. So we've been kind of in this space where we've brought the architecture to about a TRL4. We've done a lot of laboratory testing. A lot of prior research. We've done a lot of analog testing, so proof of principle at scale, to basically essentially prove and then model the system. And all of that has become an iterative process. Um, but that's how you can get away with having very lean, very low capex while you're understanding this changing of the paradigm. And then what happens is that now I can enter into the equation asking for funding for for full development of the power propulsion system, the airframe itself. All of those individual components now have their place in the development life cycle. But now that we've understood it, as these have an intention to go into this system, this is where you end up getting these gains that bring you to more of a competitive space. So I don't know if that particularly answers your question directly. I know you were asking more about design for manufacturing, but I think the core statement I'm trying to make is that it's all. It is literally, it's not just designed for manufacturing. It's not just designed for performance. It's not just designed for economics. It's all of the above. Each one of those components has to be understood as its particular dimensions overlap. And once you do it, when you do it more mentally and you do it in like a high speed of evolution of the system itself, you don't waste a lot of money trying to build components that are hopefully going to, be the holy grail of component. Because if you actually do the modeling, you see that if I were to make the most ridiculously 100% efficient, super high power density proton exchange membrane fuel cell and electric motor, if there's no real overlap of usage of energy, you really only get these first order gains. I mean, it only really appears in terms of maybe 100 miles, maybe 200 mile gain for a specific aircraft's size. But when you start going into this overlapping space, is when you really start seeing these multiplicative step change gains, where you start going from like 500 to thousands of miles. So
So it does answer the question. I guess the second question after that, you mentioned that you were going around talking to investors and that they were talking about de-risking, that they needed something more to de-risk, and I didn't quite catch what you said after that.
I try and remember what I said. One of the issues, it's not as so I've stayed intentionally away from I've stayed intentionally away from um the VC space because the VC treadmill. So they're predominantly focusing on defense appropriations and, AFWorks and SBIR, et cetera, and a lot of those contract spaces. The issue is that going back to what I was saying about Kelly Johnson, um, and Colonel Boyd, whatever his last name, I can't remember his name. They ran
I think it
into
was
sort of
John
that's
Boyd.
Don Boyd. Thanks. Um, so they ran into these issues bureaucratically where the Defense Department really likes to de-risk by tech block. And we weren't always like that. So the Defense Department used to actually make things based on programs, and this is where you end up getting the U-2 spy plane and the SR-71. But even at the time when they were doing that, when Kelly Johnson had brought these concepts together and they, created Skunk Works, et cetera, he was still fighting the bureaucracy. So going all the way back, this is why I'm saying, so this entire point of this lecture is to really understand this as a mindset. And that's kind of what I was saying about you run into these de-risking of, you run into these de-risk by component because a lot of these are, we want to have a widget that we can put into an existing system. And again, I mean, this is time immemorial as everyone that's been a holistic thinker has fought against this. So that's the issue that you sort of run into. And that's sort of what needs to be recalibrated. It's a reason why I've kind of stepped into more of the public speaking spaces is that not only do we need, because I have no problem in the scientists, so STEM professionals, they all understand holism for the most part, to varying degrees, of course. But it's now we have to enable the communities of engineers that are out there that understand this. We need to get everybody on the same sheet of music, and then we really have to now start educating the bureaucracy that's out there and also the investor community that this is the way we need to be thinking about how we create technology. So moving into the future, we've pretty much as humans have really kind of gathered all the low-hanging fruit already. So now we're moving into these spaces that require really good systems, holistic integration and understanding. So that's kind of where I was sort of going with that is that we're stalled. We're stalled essentially at um, getting these to a space where they understand that you cannot just throw this into the market. It doesn't exist without the entire system being competitive to what already exists. That's going to take a tremendous amount of work to change the mentality, or at least to get somebody to believe enough to to part with resources. So yeah.
Thank you, Jared. I know we're going a little bit over. There was one question from Albert and wanted to be respectful of your time and everyone else's time. Jared, do you still have a few more moments to answer Albert's question?
Yeah, no, I've got plenty of time.
Okay.
So
Just to
there is,
clarify, my question is for the entire propulsion system. Forget about the flight part, but in terms of the interconnection of all these components to use all the features of the hydrogen, uh, have you or any plan to test it on a brass board system stationary just to make sure
yeah,
they will work the way you're saying?
yep. That's actually what we're working on currently. So our primary focus is power and propulsion at a scaled version. So the propulsion system for the aircraft itself, the power and propulsion together and the entire electric system is 2.4 megawatts in order to give us the performance that we want. We have scaled down. So the propulsor itself is 900 kilowatt propulsor. We've scaled it down to a 250 kilowatt single system. And that's essentially kind of what we're looking for. So we're moving into the funding spaces for that. And then it will go directly into what you said. So it's a proof of concept of the propulsion system all together integrated. So that'll include the combined Brayton cycle turbine, the fuel storage system, and the high temp superconductive motor attached to the ducted fan and nozzle system. We We'll likely not put it all together to begin with. We're going to have to obviously vet the electric motor and the gas turbine, et cetera. So each one of those components is going to have to have its own vetting process, and then we're going to put it together. But that's actually what we're specifically working towards. The platform itself is going to become an emergent technology. It's necessary to do it this way, but I'm not anticipating that to be accomplished anytime soon at full scale. Most of this, the conversations that I was having with Northrop a few months back, and their interest in a couple of the other operators, everybody has sort of their own idea of what they want to see. So they want to put a propulsion system into an existing aircraft, and they want, they want to put the power system in with an existing propulsion system. So there's a lot of this patchwork that's emerging, which will help us vet each individual component, but we retain that holistic systems perspective as we've already created the digital twin for the entire architecture. So that's kind of where we're at right now.
Sounds good.
Wonderful. Thank you again to everyone joining today's webinar. Once again, thank you, Jared Semik, for your time and expertise. You had such a wonderful presentation. Of course, also don't forget to join Flying High. I'll include registration links below. And if you register before June 30th, you'll get 25% off of your ticket. Again, have a wonderful rest of your day, everyone. And thank you again for joining. Bye.
Thanks.